Alrighty, and with that, good morning everybody. Welcome back to Calc 2. What's the plan for today? We're going to start off with some class talk, and then jump into Standard 10, where we're going to be looking at sequences of real numbers. I've got my usual office hours for the next few days, from 11 to noon and 1 to 2. And this morning I also posted a new web work assignment, homework 14, which will be due Friday. Plan, by the way, is to finish off the Standard 10 quiz, finish off Standard 10 discussion in class Wednesday, so we'll have a Standard 10 quiz on Friday, is the plan. Any questions or comments before we get started for today? Yes?
Can we take a quiz over, not we, like personally come in to take a test with you in office hours over Standard 10 on Thursday?
I would allow it. So, mathematician, a physicist, and an engineer. We've reached that portion of the math joke book, by the way. Mathematician, physicist, and engineer given identical rubber balls one day, and they're each told to find the volume of the rubber ball. The mathematician pulls out some measuring tape, records the circumference of the ball, divides by 2 pi to find the radius, cubes that, multiplies by pi again, and finally multiplies by 4/3, thereby calculating the volume. The physicist gets a bucket of water, places 1 gallon of water in the bucket, drops in the ball, and measures the displacement of the water height to 6 significant figures. And finally, the engineer writes down the serial number of the ball, goes online, and looks it up. Goofy engineers, I tell you what. Alright. Y'all ready for some class talk? So what do I mean by class talk? Well, you may have noticed that the schedule of courses for next semester in the summer came out last Friday. And so what I thought we could start class off today by doing is I'll talk briefly about what are some of the upcoming math classes that are being offered in the summer and the fall, and what in particular do I think makes for good follow-up courses to Calc 2. So I know some of you are considering going on and taking further courses in math, and I just want to give everybody my thoughts as to what's out there, what makes for good follow-ups. So in the fall, if you're interested in going on in math, there's 3 basic math courses that you can take coming out of Calc 2. There's Math 310, which is linear algebra. There's Math 320, which is multivariable calculus. And there's Math, I forget the number, 330, which is number theory. And these are the 3 math courses I would say that are coming up in the fall that would make for great follow-ups to Calc 2. So the top 2 courses, linear algebra, multivariable calculus, are basically the gateway courses to the rest of the math major. Pretty much all of our upper level 300 and 400 level math courses will require either linear or multivariable calculus, or both as prereqs. They're both offered every semester. Linear algebra is focused around kind of mathematics of matrices. So in linear algebra, you do a lot of like, hey, let's take a bunch of data, put it in a rectangular matrix of numbers. We multiply matrices, find inverses of matrices, and kind of look at how do linear transformations mathematically represent a lot of useful information for us. And I've got to say, hands down, I think if you ask everyone in all the math professors what math course is the most important, they're probably all going to say, most of us are going to say linear algebra. Because, oh my gosh, linear algebra is useful in so many different contexts. Whether you're in math, if you're in physics, if you're in, say, chemistry, linear algebra is a good one to take. Multivariable calculus is kind of the other, what I would call, gateway course to the rest of the math major. And, in multivariable calculus, you'll hear a lot of us call it Calc 3. Basically, Calc 3 is like Calc 1, but in 3 dimensions or higher. So, all the functions and such that we look at in this course, just like in Calc 1, are functions that go from R to R, functions that take in a single number as input and spit out a single number as output. Multivariable calculus, you look at functions that, say, take in 2 numbers as input and spit out 4 numbers as output. And it turns out that having functions that do something like that can still be incredibly useful. And creates a lot of zany-looking graphs. You can ask a lot of the same questions that we have already with, like, what does it mean to take the derivative of a multivariable function, so to speak? What does it mean to integrate a multivariable function? What are a lot of the applications of doing these sorts of things? Another super important class for studying what I would call higher level mathematics. It's also offered every semester. If you're serious about going on and studying math or physics for that matter, or really chemistry, these are the 2 math courses that I highly recommend you take as soon as you can. Any questions or comments thus far? So the other course I have listed here is number theory. It's listed in the course catalog and officially as theory of numbers, but that's a stupid name. It's no one outside of Hillsdale calls it that. It's number theory. Number theory is typically offered every 2 falls. I say typically because Dr. Webster really wanted to teach that instead of what was supposed to be offered in its place, non-Euclidean geometry. So I'm just going to say every 1 to 2 falls. It's not in every semester course. And number theory is different from the first 2 courses in that number theory is kind of designed as an introduction to proof writing course. So you kind of talk and learn about how to write mathematical proofs, how to construct logical arguments, which we've talked a little bit about in here, but I've never really made you all do formally on like a quiz or an exam, right? Like a full formal proof. Number theory, you kind of learn how do you actually go about doing it. And the kind of the mathematical topic you study in number theory while doing that is looking at properties of the integers. Looking at a lot of things like what integers are prime, how do you determine if an integer is prime or not? What can we say about properties of the prime numbers? Are the sorts of questions that you look at in number theory. So everything else has either a Math 310 or a Math 320 prereq, which if you're taking Calc 2 right now, you don't have, I assume. Because all of these have Calc 2 prereqs. The one other course I'll mention is a course that's going to be offered in summer session 1. And that is Math 375, which also is cross-listed as Econ 375, and that's game theory. Which is offered every summer, as well as once per 2 to 3 years in the spring. And game theory is a course about rational decision making. So Debbie, let's say you and I are criminals.
Yes.
I thought you'd approve. But we're not very good ones because we get caught. They put us in separate jail cells. And we're both offered the option to rat each other out or not. How do I make decisions that'll benefit me while keeping in mind that Devin will be making decisions that ultimately will be to benefit him in such a way that we can kind of maximize either our individual or our joint utility. Or
Compare the punishment with my capacity for vengeance.
exactly. Other kind of things is looking at why are monopolies so powerful, both in the board game and in real life. Looking at topics like how does it make sense to choose something randomly in order to maximize your own utility? These are all the sorts of questions that game theory looks at. And that's a course that you can take that's offered by the math department, but you can either receive credit in the math major or in the math program or in the econ program, depending on where you want that credit to be applied for you. So this is a really good one if you have any interest in, I would say, economic theory. Also a good one if you're interested in kind of the more applied side of math. How can I use math to maximize my own utility, to make me money, that sort of thing. Yeah, that's what's coming up in the math department. Any questions or comments about any of those? Yes, Devin.
So it's not quite.
Also, Devin, I need to respond to your email still, I realize. My apologies, I'll do that later.
Always forgiven. Not quite for these classes, but how regularly are both real analysis and abstract algebra offered?
Abstract algebra is every fall, real analysis is every spring.
Okay.
I don't have abstract algebra listed for the fall because technically that has a Math 310 prereq, and unless you have a good reason, which let's have a conversation about that, you should not be taking real analysis without linear algebra, or that you should not be taking abstract algebra without linear algebra. You should not be taking real analysis without multivariable calculus. Thanks.
How often is discrete mathematics offered, and what are the prereqs for it?
Discrete math is just a Calc 2 prereq, and it is offered every spring.
Okay.
So discrete math is another sort of intro to proofwriting course. We sort of have three of them in the department: number theory, non-Euclidean geometry, and discrete math. They all kind of fill the same boat of learn how to construct formal mathematical arguments, but kind of looking at different types of math problems along the way. And I would just say discrete math is probably the intro to proofwriting course that's kind of the most focused towards applied mathematics, like using math to solve real-world problems. Okay?
Same question, but for differential equations.
Differential equations is the plan is to have that be offered every spring. I say that's the plan because prior to this past year, it was only every other spring, but we're going to make it every spring going forward. Differential equations is sort of like Calc 4 almost. It'd be like if I were to say, hey Jonah, find all functions f of x such that f of x plus f prime of x minus 2x times f triple prime of x is equal to 0. And it turns out that there's a lot of practical applications to why would you want to find functions that satisfy equations like this. I don't know why I'm picking on you, Jonah, when Gabe's the one asking the question. But that is an every spring course, and that does count towards the applied math major. But HAT does have a linear algebra prereq. I will say, the department does offer majors in both pure mathematics and applied mathematics, whereas pure mathematics is kind of studying math for math's own sake, looking for the inner beauty of math, whereas applied mathematics is how do I use tools for math to solve real-world problems. Both of these top two, I would say, kind of fall under both categories. You need both of those for both majors. Number theory is more of a sort of pure studying math for math's own sake type course, and game theory is very much an applied math, using math to solve real-world problems type course. If any of you have any questions that are kind of more individual about, like, Dr. Gerstel, which course do you think is right for me given my interests? Be happy to happy to talk with you in office hours or over email. Give you some more personalized advice on math courses. All right. Anybody else before we jump into Standard 10? Let's jump into Standard 10 then. So, 4, 5, 6. So, last time we kind of talked about some motivation for the rest of the semester regarding kind of like Zeno's paradoxes, the paradox of how can you add infinitely many numbers, and like 1 + 2 + 3, etc., and get a finite answer like -1/12. Which is really weird. And what we're going to be building up towards that. So in Standard 11, we're going to start asking the question of looking at infinite sums and determining when do these infinite sums converge to a finite number or diverge, sort of like what we did with improper integrals. But before we get into looking at these sort of infinite sums, we need to talk a little bit about sequences. Where because infinite sums are going to be defined in terms of sequences ultimately. So sequence is just like an ordered list of numbers. So like you got 1/2, 2/3, 3/4, 4/5, 5/6. For instance, we could say that's going to be what's in math called a sequence of real numbers. You just take infinitely many real numbers and kind of line them up in order, going from left to right. And the order doesn't have to be they're getting bigger or they're getting smaller. It can be whatever order you want them to be in. So let's take a look at this sequence to start. 1/2, 2/3, 3/4, 4/5, 5/6. So the notation we oftentimes use when we're talking about sequences is we'll call them like a sub n. And in the individual terms will be like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and so on. So the first term in the sequence is 1/2, the second term in the sequence, a sub 2, is 2/3, etc., etc. Can anybody give me a formula for if I wanted to ask you what's going to be the 100th term in the sequence? What would you expect it to be if we were to write out the 100th term in the sequence? If the first term is 1/2, the second term is 2/3, and so on. Jonah?
100/101.
Yeah, I would say that a sub 100 we would expect to be 100 over 101. And if we wanted the 32nd term, we would probably say 32 over 33, and so on. How can we write a formula for the nth term in the sequence as an expression in terms of n? Phoebe?
Is it n over n plus 1?
N over n plus 1? Bethany and James, you on board with that? I am as well. Yeah, we could say that the nth term in the sequence is always going to be equal to n over n plus 1. Where then you can replace n with whatever number you want. You could replace n with like 50 to get the 50th term in the sequence, or n with 99 to get the 99th term in the sequence, and so on. Any questions or comments about any of the notation used in talking about these sorts of sequences? This is notation, by the way, we're going to be using for the rest of the semester pretty heavily. So what happens as n goes to infinity? Meaning if we look at the terms in the sequence as n gets larger and larger, meaning we go out further and further and further in the sequence. What do you notice about like the individual terms? James?
They get closer and closer to 1.
They get closer and closer to 1. Phoebe, would you agree? So in other words, if we start graphing out these terms, let's say here's 0, here's 1, we're going to have a sub 1 is a half, so that'll be about right here. A sub 2 is 2/3, well, that'll be about right here. A sub 3 is 3/4, okay, that'll be right here. A sub 4 is 4/5, and so on. And if we keep drawing dots, we're going to get dots that look something like, well, something like that. Picture infinitely many dots. It looks like the individual terms in the sequence are getting really, really close to 1. Like a sub 100, for instance, 100 over 101 is a fraction that's smaller than 1, but only very, very slightly smaller than 1. Whereas something like early on in the sequence, a half, that's still fairly far away from 1. It's just as close to 0 as to 1. But as n gets bigger and bigger, a sub n is going to get closer and closer to 1. And we can even say the sequence a sub n converges to 1. How about this other sequence? Let's look. How about if we look at the sequence b sub n is going to be the sequence 3, 1, 4, 1, 5, 9, 2. How much did I actually write down? 6, 5, 3, etc., going on forever. So this gives us another perfectly valid mathematical sequence of numbers where the first term, b sub 1, is going to be 3. The second term, b sub 2, is going to be 1. The third term, b sub 3, is going to be 4, and so on. First of all, does anybody recognize the individual terms of this sequence? So I assure you, I didn't construct this randomly. Oh my gosh, I did it again. Why do I want to keep calling you Anna? I'm sorry.
It's the digits of pi.
Yeah. So b sub n, we could say in this case, is going to be the nth digit of pi. Because if we write out pi is 3.141592653 ... By the way, that's all the digits of pi I have memorized. I'm sorry, I'm not a true math nerd. I don't have like 500 digits of pi off the top of my head. But what can we say about what happens as n gets bigger and bigger? Over here in our first sequence, our a sub n sequence, we said that as n gets bigger and bigger, it looks like all the numbers in the sequence are going to be getting closer and closer to 1. That the sequence converged to a value of 1. How about this sequence? Do the numbers look like they're going to converge to anything specific? Joy, what do you think?
No.
Does it look like it?
No.
It doesn't look like it to me either. Technically, this could converge. Mathematicians don't actually know if the sequence actually converges to anything. It could be the case that past the first 5 gazillion digits of pi, suddenly the rest of the digits of pi are all like equal to 3 or something. We actually know that doesn't happen, but we don't know infinitely many digits of pi. Pi goes on forever, and it never kind of slowly repeats itself. But one thing that we do know as mathematicians is that v sub n, we can say, diverges. And that it doesn't converge to any single finite number. Seen these terms converge and diverge before in this class, because they've shown up in one of our previous standards. Anybody remember the context in which we talked about whether something converges versus diverges? And James?
Improper integrals.
No class. You have a quiet class when you have to call on James. Yeah, improper integrals was kind of the other scenario where we've seen these words converge and diverge before. And in this context, converge and diverge are going to mean something very similar. With improper integrals, we said that an improper integral, where we're integrating over one of these regions with an infinite surface area, or an infinite perimeter, so to speak. We said that an improper integral converges if the integral comes out to be equal to some finite number, or that the improper integral diverged if it had sort of this infinite area contained within it. If you tried to integrate and the answer came out to like plus or minus infinity, for instance. Same's generally going to be true for sequences. We're going to use the same words, converge and diverge, but with a sequence, we're going to say that a sequence converges, and I'll make a note of this on the sideboard. We're going to say that a sub n, the sequence converges to, let's call it a finite number L, and I'm on the second page in the packet now, for those of you following along there. If, as n gets larger and larger, the individual terms in the sequence are going to get closer and closer to L. So in this case, on our sequence on the first page, our a sub n sequence, we said converge to 1, because if you look at very large values of n over n plus 1, the nth term in our sequence is getting extremely close to 1. In fact, we can say that the limit as n goes to infinity of a sub n, in this case, it is equal to 1. Saying that as n gets larger and larger, the sequence has a limit of a finite number, which is 1. So, if that's what it means for a sequence to converge, what do you think it means for an individual sequence to diverge? It converges to a number if, as n gets really, really big, all the terms in your sequence are going to get really, really close to that number, some number L, which we'll call the limit of the sequence. If you had to guess, what would you say it means for a sequence to diverge? Bethany?
That like the numbers don't come close to like a single finite number. They kind of all over the place. Or
Yeah, no, that's a good way to think about it. Basically, and this is a little bit of a cop-out answer, a sequence is divergent if it isn't convergent, if it doesn't converge to a single number. So b sub n, we can say diverges if it does not converge to any single number. So a good example would be like b sub n, would be like this b sub n sequence from the front page, where the digits of pi. Whereas Joy pointed out, the digits of pi don't all seem to converge to a single number. They're kind of all going to be all over the place between 0 and 9 as n gets larger and larger and larger. So you could have these sort of chaotic sequences. Sequences that aren't kind of getting close to any individual numbers. What would be another way that a sequence could diverge, other than sort of this random chaotic behavior, like the digits of pi? Gabe?
You could just go to infinity.
Yeah, you could also have a sequence that goes to infinity. So what would be an example, Gabe, of a sequence that does that?
All the real numbers.
All real numbers. All real numbers, you can. How do you propose we write out a sequence of all real numbers?
Natural numbers on natural numbers.
Ah, the natural numbers. So like 1, 2, 3, 4, 5, etc., etc. So that would be, yeah, an example of a sequence that goes to infinity and thus is divergent. Aiden, do you have a sequence in mind that diverges to infinity?
Like an oscillating function, like 1, -1, 1, -1 repeating.
Ooh, okay. I'm not going to write that one down because I'm pretty sure I have that as an example later in the packet. But that would be another example of sort of a divergent sequence, where the terms are following a well-known pattern. They're not really going to infinity because if your numbers are only 1 and -1, that's not getting infinitely large, so to speak. But that would be another example of something I would say is divergent. Any other questions or comments about sequences and what does it mean for it to be convergent or divergent? Alright, in that case, you all look like you need some activity time. So, what I want you to do is I have a bunch of sequences on the next 2.5 pages of this packet. So pages 2, 3, and 4. Ending with the sequence e sub 1 equals 1 and for each n greater than 1, blah, blah, blah. What I would like for you all to do is to take a couple minutes, and as always, you're welcome to work with your neighbors. For each of those sequences, see if you think whether or not that sequence converges or diverges. And if you think it converges, what value does it converge to? So pages 2 through 4 in the packet, go ahead, take a couple minutes, and see what you think about each of those sequences, whether it's going to converge to some number or it's going to diverge. sorry, my mistake. The sequence I had in mind was 2, -2, 2, -2, 2, -2, not the one you had in mind, but pretty similar. Oop, there's a typo in the last one, by the way. It should say -1 plus E sub n minus 1 all over 2, not -1 plus F sub n minus 1 over 2. That's a typo. As always, feel free to ask me questions or to talk to each other as you work through this. If you feel like you have answers to all of these, turn to your neighbor and see if they agree with you.
Are you done yet?
The last one.
It's okay.
You get it?
I think so at least.
How we doing on case?
Just going to push it back and forth so it's the same question.
I would say so. Particularly because this is always going to be 1, 0, or -1, right? If n is an integer. Or a natural number, however you want to spell it. questions, and one definitely is a little bit trickier. Now, whenever someone annoys you, sometimes feels good to just give them a good hiss. Goodness. I know the feeling. Although usually my feeling is my brain's going too slow. Yeah, I would say so. If you're ever unsure about it, you can also always just start plugging in numbers, like plug in n equals 1, 2, 3, 4. I know it's trick. Nobody wants to plug in tricks, but yeah, I would say so. No, you don't know why I developed an Anna Alley complex for the two of you.
Oh, yeah.
I've known your name for a while now.
Oh, yeah, that's good.
Converted?
I don't know,
Yeah.
these
To negative one.
these two-syllable A names are getting.
Because, so the first one is 1, then after that, it's -1 plus the last term you had.
Yeah.
So, -1 is 0, divided by 2, so the second term is 0.
Oh, yeah.
Yes.
Yeah. I did it wrong.
Yeah, because each one you just add 1 to it and then multiply the bottom by 2. So,
Yep.
Last one. Last one's definitely the trickiest, I would say.
Wait, tell us how you add 1, 3.
well, so you add 1, which
Multiply
is,
divided by 2.
Say what?
well, you're adding -1, I guess, but, so adding -1 to add it, you have to add it by like the thing, so -7/8 would be plus 8/8.
The 1/2.
The first one I just put converges to pi,
I guess that's true, yeah.
because pi is the same number.
Yeah, that's true.
Good question.
The next
Would
one's
you
divergent.
still say
Yeah.
that as ink gets really, really big,
This one's divergent.
Yeah.
This one I have converges to 0.
Yeah, so that converges to 0 too.
How about if I gave you this?
But I think you might have said that it was
Did you?
No, I averaged to 0.
Wait, what was that?
What if that converges to 0
Well, because this one's in the numerator, as n gets bigger and bigger, it'll be 2 to the bigger and bigger power, which will just shoot off this way. But this one's 1/3 to the n, so the 1 will stay the same no matter what power it goes. But the 3 will get bigger and bigger, So then you always have a constant 1 on the top over a number that's getting bigger and bigger as it progresses. So that'll get closer.
So basically, it's the same sequence, I'm just changing the first term. So literally,
That's true.
instead of negative two.
I don't think 10 can't be
Turns
negative.
out the first two terms don't really kind of last. We're gonna have a discussion about that.
Or maybe that's really big one.
Yeah, that's just
Usually,
n minus
that's
1
less concerned with the first two terms, it's more what's kind of the pattern, very small about it.
Yeah.
Very small, but
Yeah, and then this one I think is divergent because the negative part is
Actually, I said it could go to 0. I said it goes to 0.
oh way.
And it's negative 1, 1/2, negative a third, 1/4.
Yeah, because it's negative. It's always a
It's
negative
slipping back and forth, but it's getting
on the
closer.
top,
Yeah.
which one are you looking at?
it's getting closer to 0.
Yeah, but it's popping like closer. It's kinda cool.
So it wonders. Yeah, that's divergent.
I think it is.
It has to be greater than 1, because here, I explicitly saying e sub 1 is 1. I'm giving you the first value, and then saying every value in the sequence past the first value is defined in terms of the previous one.
Okay, so. I think
So I would say
That's just.
Yeah, then the last one I just put divergent.
it is weird.
Or, yeah.
We're gonna talk
It's
about
not,
it.
it's not a great reason to have an issue with something here.
Yeah, but-
No, that's a great reason. Something being weird and unlike the others, because all these others I can use
Because it's
the
not
formulas for here's the is term.
likely that.
Other than these two, which there's a easier to see pattern, this last one's definitely is a tougher pattern, I would say.
And then the next one would be cosine over 2 pi or 2 cosine pi, which would be. Oh no, the first term is 0, the second term is -1, and the third term would be
Just
0 again, and the fourth term is positive.
Oh,
Then
yeah.
just
It
like
actually comes out to along the line of zeros, because if your second term is 0, what's -1 plus 0 over 2?
So that's just the thing, unless I'm screwing back up, I end up getting the entire numerator is 0.
For n equals 2, yes, but that doesn't mean you're going to keep getting that for n equals 3, n equals 4, and so on.
Hold on, so when we're adding 1, is that supposed to be to the numerator as well?
Can I see the packet? So what we're doing is, for n equals 2, you're right to take -1 plus previous term, so 1 over 2. But if you wanted to do n equals 3, e sub 3 would be -1 plus e sub 2.
Oh,
All over
okay,
two.
so we're adding that from the beginning all the way through.
Right, you're always adding the previous term to -1 and dividing by 2.
Okay, I was starting from the middle.
Oh, yeah, no, don't do that, it's always a previous one.
This one?
Yep.
So both, like, it'll always be a -1 or a +1 on the top, but each one will get closer and closer to 0. So is that still convergent if it's like going different ways?
I don't know, have you tried graphing it out? So like, what would that give you? -1, a half, -1/3, a fourth, -1/5, a sixth? Are all those terms getting really close to 0 as n gets bigger and bigger?
Yeah.
I would say it converges to 0 then. Even if it's not strictly increasing or decreasing necessarily. This is an example of a counterexample to a lot of sequence theorems, by the way, or a lot of sequence statements, because it's oscillating and yet it still can manage to converge. Things going okay back here? Doing well? Cool. Alright, sounds like the discussion's sort of dying down, so let's take a few minutes and talk about these as a class. Get your all's thoughts on these. So, how about this first sequence? The sequence 3, 3.1, 3.14, 3.141, etc., etc. Sort of like the second sequence from the front page, and that this is very much related to pi, maybe, I don't know, possibly in some way, but it's defined a little bit differently. So for each of these, what I want to do is I want to do a vote by thumb. thumbs up if you think it's convergent, thumbs down if you think it's divergent. So for this one, 3, 2, 1, vote. Ooh, already seeing some controversy. Nathan, why do you say yes?
Yes, maybe convergent.
Yeah, why? Yeah. So why do you think? Or first of all, what do you claim the sequence converges to?
Pi,
Why do you think it converges to pi?
because it's closer and closer to what pi actually is.
Okay, interesting. Joanna, why did you say divergent?
Because isn't it technically going to infinity? Like it's gonna go to pi, but pi is infinite, so it's not like one.
Is pi infinite?
I think so.
Well, let me ask you this. What do you mean when you say pi is infinite?
Like it's never gonna just stop at one number. So
Ah, okay. That if you were to write out a decimal expansion, the decimal expansion never ends, so to speak? Yeah, I would certainly agree with that statement, that if you tried to write out pi as a decimal, that decimal would never end. But Nathan claims that he still thinks the sequence converges, and that it converges to a value of pi. James?
Well, if you look at the rules of what it means to be convergent, it never says that it has to be rational. So it could still converge to an irrational number. And this is defined like as pi, just getting closer and closer to pi each time, which is the definition of convergent.
I think I would agree. This actually does converge to the value of pi. And I agree with Joanna that pi it has an infinite decimal expansion, that you need infinitely many digits after the decimal to kind of fully write out pi. Good luck trying to do that. But pi is still a finite number in the sense that pi isn't like equal to infinity or negative infinity. If I wanted to draw out a number line, like 0, 1, 2, 3, 4, pi is not going to be extremely far to the right or to the left. In fact, it's going to be about right there. So even though we're getting numbers with longer and longer decimal expansions here, I would still say that the sequence itself still is going to be convergent with a limit of the finite number pi. This is an interesting example, by the way. We've talked a lot about this example in my real analysis course that I'm currently teaching. This is an example of how you can have, as James pointed out, a sequence of numbers that would have, of nice numbers, rational numbers, numbers that can be written nicely as fractions, that converge to something irrational, something that can't be written nicely as a fraction like pi. Yeah, Phoebe?
If you didn't know pi and that wasn't really on the table, but you kept adding decimals, would you say it converges to 4 because it's getting closer and closer to 4, or do you have to?
Well, if you didn't know pi, so if pi was off the table,
Yeah,
then I would say you have a hole in the real numbers, and this doesn't converge to anything at all. I would say it doesn't converge to 4 because if you look at even numbers that are really far out, like 3.141592653, is that really all that close to 4? I would say kind of it isn't. I would say this looks a lot closer to, for instance, 3.15 than it is to 4. Because even if you keep adding decimals out, you're still going to be about 0.86 away from 4, no matter how many points after the decimal you add. So I would say this is never going to really converge to 4. In my real analysis course, we actually talk about what happens if you take pi off the table by only saying that we're allowed to work with rational numbers, for instance. And in that case, what I would say is, well, if you can only work with rational numbers, this doesn't actually converge to anything. It would be divergent. But for the purposes of this class, this is a sequence that converges to pi. Good question, though. Anybody else? this one? 2, -2, 2, -2, 2, -2, alternating back and forth between 2 and -2 forever. So thumbs up if you think it converges, thumbs down for diverge. 1, 2, 3, vote. I've seen a lot of thumbs down here. Reagan, what do you say thumbs down?
I said, to be honest, I said thumbs down because earlier someone gave an example and we determined that osculating was diverging.
Thank you, Aiden.
But I don't actually know number-wise, like why. I didn't figure that out.
Okay, fair enough. Yeah, this looks a lot like this 1, -1, 1, -1 example that we said earlier diverge. So if that diverges, this probably does as well. Let's see. Christopher, what did you think about this one?
I said it's divergent because it doesn't converge to a finite number.
Yeah. So if we tried to graph out what do the individual terms in the sequence look like, we'd sort of have, oh hey, up here at 2, we'd have a dot corresponding to a sub 1, as well as a sub 3, a sub 5, a sub 7. We'd also have a dot over here at -2 corresponding to a sub 2, a sub 4, a sub 6, etc., etc. My goodness, someone's really trying to call me right now. Sorry, my pocket's buzzing on me. Does it look, Reagan, back to you. Does it look like as n gets larger and larger and larger that all the terms in the sequence are getting really, really close to a single number?
No.
It does not. I would say this is also, I think I would agree with everyone and say this is a divergent. The terms don't all get close to a single number. Any questions or comments on that one? How about a sub n equals 2 to the n? That would be like the sequence 2, 4, 8, 16, 32, etc., etc. Thumbs up for converge, thumbs down for diverge. Thumb sideways for I'm too scared to make a stance. This wasn't my one good piece of chocolate. Toss it at me. Aiden, why do you say no?
Because 2n, 2, 4, 8, 6, it just gets larger every time we go. It doesn't seem to slow down at all as far as progression goes. It just goes infinity.
And it keeps growing, and it keeps growing at a faster and faster rate too. It almost looks like if we were to look at like y equals 2 to the x, for instance, that's an exponential function. That's something that grows really, really fast. Gabe?
If we say that n can only, the smallest value of n is 1, can we say that the series or the sequence converges to 2 on like the front half?
Ah, on the front half. So if you took the same sequence but sort of going backwards, so to speak, you couldn't really do that because you can't really, because some deal with sequences is you can't really have sequences that start with infinitely many numbers but then end at a finite number. It's always the other way around. You always start at something at a single number and then it goes on forever going to the right. If you had a sort of reverse sequence, and yes, that is a thing in math, it's not something we're doing in this class, but it is a weird thing that can happen in math. It's called a cosequence. Then you could say that converges to 2, but we're not going to talk about those in here because that's a very advanced topic. Good question. Yeah, I would say this is going to diverge. And if you want to say how it diverges, you could say it goes to infinity. How about 1/3 to the n? Show of thumbs. Converge or diverge? Anna. Yes, I think I got it right this time. What did you say converge?
Because the number continues to get smaller going from 1/3 to like 0.11 to 0.037, so it kind of converges to 0.
Oh, you're giving me some decimals, huh? Yeah, if we started to write out individual digits, we'd get 1/3, 1/3 squared, which is a ninth, 1/3 cubed, which is 1/27, 1/81, etc., etc. And you're saying that those values look like they're getting closer and closer to
0.
Everyone on board with that? I would agree. This one actually converges to 0. You notice these two sequences are defined similarly. We're just taking constant number to the nth power. This one diverges. This one converges. Color me intrigued. How about c sub n equals -1 to the n all over n? Converge or diverge? 3, 2, 1, vote. Bethany, why a thumbs up?
Because if you look at like the numbers, if you like update them, so it's like -1, 1/2, -1/3, 1/4, like they're both getting, even though one's negative, one's positive, they're both getting closer to 0 from both sides.
Interesting. So you're saying like we sort of have an oscillating sequence, but the oscillations are getting smaller and smaller so it can still converge to say 0? Yeah, so if we were to try and graph this out, we would get something like dots that sort of look like this. We'd have one at -1, 1.5, one at -1/3, one at 1/4, one at -1/5, and so on. And so even though this is an oscillating sequence, it oscillates back and forth between positive and negative numbers, sort of like this 2 example from earlier, I would still say that this sequence converges to 0. Because this sequence, the oscillations don't get smaller. It's just the same oscillation. It goes back and forth between 2 and -2 every time. It never gets close to anything. But that one, the oscillations kind of zero out over time, so the sequence can still converge to 0. All right, we'll pick things up from there on Wednesday's class. So Wednesday's class, we will finish talking about sequences. And if we have time towards the end of class, start talking about infinite sums, like from last Friday, but a little bit more formal. Y'all have a good one. See y'all on Wednesday. Don't forget, if y'all want to talk classes with me, be happy to have a more personalized conversation with you. Good one. Okay, yeah, sounds good. Yeah, I have things to say to you that I didn't actually put in an email because I got distracted.
Well, I think I have again, I told you the story about the straw.
Yes.
I have an idea.